Now we're going to look at what happens to a charge in a magnetic field. This is the first object that we're going to talk about that has a reaction to the magnetic field. So when a charged particle is moving through a magnetic field, a magnetic force acts upon it. So that magnetic force is that F. Often we'll give it the subscript B. It can only act if it's moving through a magnetic field, and we'll get into why that is when we get to the mathematics, but it has a velocity. And these lines show the magnetic field. The force has a maximum value when the charge moves perpendicular to the magnetic field lines, but if the velocity is along the magnetic field lines, then the force goes to 0. The mathematics of it to calculate the force on a moving charge is equal to the force times the velocity times the strength of the magnetic field. Now the unit of magnetic field of B is a Tesla typically, which is defined as a Newton per amp meter. But the formula we're going to use, since I have not taught you how to do cross products properly, we are going to use V times the sine of theta, where the theta is the angle between the velocity vector and the magnetic field vector. Will get us good enough math that we can handle the problems that we're going to be given instead of having to do the actual cross product. So what is the result of the cross product? We talked about this back when we talked about torque, is that when we have two vectors that are cross product with each other, we get a third vector moving in the third direction. And so this is one of the right-hand rules that we're going to do, but I'll teach you the next one in the next slide. So the cross product is not commutative, that A cross B is not the same as B cross A. We'll get very different results. Now we're going to talk about the two right-hand rules. The first one I'm going to talk about is probably the more difficult one, so it might have been the one that you learned in high school. The one to pay attention to is the one on the right. So basically the original right-hand rule said that we point our fingers in the direction of the V, curl them in the direction of B, the magnetic field, and the thumb points in the direction of the force. However, I think this other right-hand rule is much easier to use. And that is, we point our fingers in the direction of the magnetic field. And that makes sense because there's lots of magnetic field lines. So you have lots of fingers, lots of magnetic field lines. And the thumb represents the velocity. And so if you're going to go hitchhiking, which I don't recommend, then you're going to point your thumb out, right? So this is your velocity. If there's one thing, you need one thumb. And then if you slap something, then that's the force. So your palm represents the direction of the force. So B is the magnetic field, B is the velocity vector, and your palm represents the force. So you can think of slapping something as the force. And that's going to be the easier right-hand rule to remember. Now, those of us who are right-handed have a slight disadvantage here because we cannot write and do the right-hand rule. I have numerous times tried to do the right-hand rule with my left hand. And guess what? I get the wrong answer. So make sure you're using right hand. If you're right-handed, set your pencil down to do the right-hand rule. Whereas if you're left-handed, you actually have a slight advantage because you can write and use your right hand for the right-hand rule at the same time. Now for the units of the magnetic field. We said already that it was called a Tesla. Tesla is defined as a Weber per meter squared, and now Weber is a unit of magnetic flux. We'll get there. It's also a Newton per Coulomb meter per second, or Newton per amp meter. So that is a Tesla named after Nikola Tesla, an Russian-born American inventor from the turn of the century. So the other unit is called a Gauss in English units. And here's a picture of all the magnetic fields around most of the planets. Sadly, Mars does not have much of a magnetic field at this point because its core has cooled and so no longer has a gelatinous iron core to create a magnetic field. So what are typical magnetic field values? Well, Earth's magnetic field is about 10⁵ Teslas. Superconducting magnets, however, are 30 Teslas. So these are MRI type machines, but conventional laboratory magnets are about 2.5 Teslas. So much stronger than the Earth's magnetic field. And here's a picture of the declination of Earth's magnetic field throughout the Earth. And here you can see the magnetic North Pole close to Antarctica. That would be the magnetic North Pole, and the different declinations of the magnetic field in the different areas. And so clearly the compass, does not always point north. So now we're going to do a little bit of math with this particular equation. We here want to find the angle of the magnetic field. So the electron moves at this speed, so that looks like a velocity, in a 1.2 Tesla magnetic field, so that's B. If at one instance the electron is moving due west and experiences an upward magnetic force, so that's our force, of this many newtons, what's the direction of the magnetic field? So we say we're moving west, the force is up. Generally we're going to represent a circle with being up because it's going to be the point of an arrowhead. We'll get to what we represent for down, but we're going to use a dot for up because now we have three directions to deal with. So now we want to solve for theta in this particular equation. So sine of theta is equal to my magnetic force divided by QBV. I put all those numbers in, 3.2 times 10 to the negative 14 newtons, divided by, this is an electron, so Q is equal to 1.6 times 10 to the negative 19th coulombs. So 1.6 times 10 to the negative 19 coulombs times 1.2 Teslas from the problem, and the velocity is 2 times 10 to the 5th meters per second. And so that gives me sine of theta is equal to 0.833. And that means theta, if I take the inverse sine, is 56.4 degrees. From this particular information, though, we can't tell if the magnetic field is pointing in this direction or this direction, with that being theta, because both of them would give us the same, basically horizontal component to force. So it could be either north of west or north of east, we can't tell. Now this is your problem to give a try. What you want to do is just solve for the force. So given the numbers in the problem, again a 1.2 millitesla magnetic field. Okay, so hopefully you've gotten a chance to figure this out. We have a uniform magnetic field that is B, pointing vertically through our volume in the room. The proton, so again that means Q is equal to 1e, and here is our speed. So we just want to put the numbers in. So we have 1.6 times 10 to the negative 19th coulombs as our Q, 1.2 times 10 to the negative 3 Teslas, times 3.2 times 10 to the 7th meters per second. And it says it's pointing straight up. So we're going to say it's a sine of 90 degrees because the electron is moving horizontal and our magnetic field is up. The angle between those is in fact 90 degrees. So if we put all those numbers in, then we get a 6.14 times 10 to the negative 15th newtons as our force. Now that might seem like a teeny tiny force, but if you put in it to this equation, the mass of the electron, it's actually a huge acceleration. So it's a huge force for a tiny, tiny proton.